Oxyhemoglobin dissociation curve or oxyhemoglobin association curve is a common topic to be questioned in basic science exams. It could either come as MCQ, SAQ or CRQ, even in Vivas as well. The curve describes changes in oxygen saturation or oxygen content of hemoglobin in relation to partial pressure of oxygen in blood. Saturation refers to the amount of oxygen bound to hemoglobin relative to the oxygen binding capacity of hemoglobin as a percentage. Four diatomic oxygen reversibly interact with hemoglobin to form oxyhemoglobin. This process follows cooperative binding, which means upon binding of one oxygen to hemoglobin makes subsequent binding of oxygen relatively easy. It gives a sigmoid shape to the curve. Important to understand that curve is interpreted in given standard conditions such as 7.4 of pH and temperature of 37 degrees Celsius and 0 base excess, where these parameters are kept unchanged. We will identify x and y axes. Scale is from 0 to 100 on both axes. X-axis is partial pressure of oxygen in blood. For practical reasons, we will label it in millimeters of mercury. And y-axis is the saturation of hemoglobin. At 100 millimeters of mercury, it saturates around 97.5. It is the arterial point of the blood. At 60 millimeters of mercury, it will saturate around 91%, which is a critical point or ICU point. At 40 millimeters of mercury, it will saturate around 75%, which is the venous point of blood. And at 10 millimeters mercury, it will saturate around 10, which is 10 point. 50% of hemoglobin will saturate with oxygen at partial pressure of 26.6, which is P50. Now we will connect the old dots, and which gives the sigmoid shape of the curve. Plateau top part of the curve represents the buffer zone of the curve, where reduction in partial pressure of oxygen will not reduce the oxygen content much. Steep slope represent the oxygen delivery part, where small reduction in partial pressure of oxygen will reduce the oxygen content significantly. Increase in allosteric modulators such as H plus carbon dioxide, temperature and 2,3-DPG will shift the curve to right side, where the P50 is increased. Fetal hemoglobin has low P50, therefore the curve is shifted to left side. Myoglobin has very low P50, the curve is rectangular hyperbola. P50 is partial pressure of oxygen at which 50% of hemoglobin is saturated with oxygen. It's a point in x-axis, not in the curve. In standard conditions of adult hemoglobin, P50 is 26.6 millimeters mercury. It is an index of oxygen affinity to oxygen carrying molecule. It facilitates comparison of oxygen affinity with other molecules or in the presence of allosteric modulators. Allosteric modulators, which favors relaxed state of hemoglobin, reduces the affinity and increases the P50, thereby shift the curve to right side. Examples are H+, carbon dioxide and 2,3-bisphosphoglycerate. It only shifts the curve to right side and will not depress the curve. Depression of the curve only seen in few animals in specific conditions. 2,3-BPG bind preferentially to beta subunit of adult hemoglobin. It reduces affinity of oxygen to hemoglobin. Fetal hemoglobin has 2 alpha and 2 gamma subunits. Therefore, 2,3-BPG has minimum effect on fetal hemoglobin on oxygen binding. Therefore, fetal hemoglobin has high affinity to oxygen and shift the curve to left side.